All right, folks, synchronous machines. And in particular, we'll start out with synchronous generators. And the reason why we start out with synchronous generators, it operates on sort of the easiest principle of how an AC machine works. It's synchronous because the fact is that the operation of the machine has to always operate in sync with the rotating magnetic field. So the speed of this thing, if you remember last class, we talked about speed of operation, 3,600 RPM, 1,800 RPM. A synchronous generator always has to operate at whatever the synchronous speed is. And it's, again, it's based on the number of pole pairs that you have. So if you need something that's going to operate at synchronous speed, like say, for example, you needed a conveyor and you were trying to operate a conveyor at a very specific speed, like maybe you were making something that had a very specific indication of where that was on some sort of a conveyor belt, then you wanted to keep that speed constant regardless of the load. That's when a synchronous machine would be a really good application. You don't see a lot of needs for synchronous machines, motors, I should say, anymore. And it's primarily because of the fact that most applications you can get by with variable speed. And if you do need an application where you need a constant speed, there are better machines that do that. Now, that's not to be said that there are synchronous motors that are running fully no load, meaning they're just spinning and not doing any mechanical work. I worked on a project a few years ago in New Hampshire. PSNH likes to use these things called synchronous condensers, which is basically a synchronous motor without any load. And the purpose of it is to support the system under heavy load conditions or fault conditions typically. What we'll start to learn as we get through the material on synchronous machines is that they're really good for providing lots and lots of fault current. So we really spend most of our time on synchronous generators, and it's because of the last bullet. You see it says large AC power works rely almost exclusively on synchronous generators. It's not almost exclusively, it's not quite as bad as that, but it's still the preponderance of your AC power that you're going to get from your wall socket is going to be from a synchronous generator. More and more we're getting renewables, right? So we're talking about solar. Those are inverter-based technologies. Also, if you talk about wind turbine generators, they can have a slightly different characteristic that they can use inverters. Excuse me. But most of them, at least in the Northeast, use what are called doubly fed induction generators, and we'll learn about induction machines next chapter, or the chapter after that, I should say. But the idea is that still the majority of them are going to tend to be synchronous. So Maine Independence Station is about 7 miles from campus. They have 550 megawatts of electrical capacity there, and all three of the generators there are synchronous generators. Now, wind turbines, the largest wind turbines that you can get now, I just recently looked at a project that they're proposing 16.8 megawatt wind turbines. I think you can get them up as high as 20 megawatts, but it's getting harder and harder to get turbines that big. And the reason being the wind only has so much power. So it's not like you can just put a bigger generator in. It actually has to have a bigger mechanical system, which means the turbine blades need to be really big. And at some point, it becomes almost impractical to build. So these 17 megawatt, 20 megawatt turbines are so massively tall with such long blades that they have to be for offshore applications. I don't think any onshore applications are more than 10 megawatts, just because you can't, they're just not practical to build onshore. So 550 megawatts at Maine Independence Station. Calpine Energy is a place in Westbrook. I don't know if people are familiar with that area at all. But if you go down to the Westbrook area, and if you're on Congress Street or Spring Street, I think, sort of the backside of Westbrook, or the front side, depending on your perspective, there's another 550 megawatt generating facility. It's almost exactly the same as the one you see here in Veazey. There is a bunch of smaller ones like Cousins Island or Wyman Station. Those are, well, Wyman is a hydroelectric facility. Cousins Island is a fossil fuel fired facility that's still operating. That's about 300 megawatts. I'm not sure how big Wyman is, but that's a hydroelectric dam. So that would be synchronous machines. The hydroelectric facilities, all the ones that I'm aware of, all use synchronous generators. So I would say probably 80 to 85% of the capacity in Maine is from synchronous generators. So is it almost exclusively? I don't know, but it's quite a bit. So a synchronous generator should be called a synchronous converter, and it converts mechanical power to electrical power. That's all it does. But the mechanical power can come from all kinds of things. It can come from steam, as in the case of providing it with a steam turbine. It can come from gas, and it's not actually from gas, right? The natural gas, what do you have to do for natural gas? What's the difference between steam and natural gas? There's one big thing. Temperature, right? The steam is at 2000 degrees, whatever the temperature is. Natural gas is, they obviously will keep it cooler, or tend to try to keep it cooler, but you don't actually get any of the energy out until you burn the natural gas. So in a gas turbine, it works very differently than a steam turbine. A steam turbine, what you have is you have the expansion of the steam, and then that reduces its energy. And then in a condenser, you take it back to water, and then you send it back to whatever the boiler is. In a gas turbine, the difference between the gas turbine and the steam turbine has to have a separate boiler. A gas turbine, there are nozzles that blow in natural gas, and then that's ignited, and then that's where the source of energy is. So the steam turbine and boiler, if you will, or the firing mechanism are all sort of one package. So steam turbines tend to be really big facilities because the boiler is so big. Natural gas turbines tend to be much, much smaller. You can put a natural gas turbine on the back of a flatbed, and it works perfectly fine. Steam turbine's not going to work so great at that. The advantage of a steam turbine is you can burn just about anything, right? If you have a boiler and they have these things called fluidized bed boilers, that is basically sand, and you blow air on the bottom, and it kind of liquefies the sand because it's under so much volume of air. You can throw anything in there. You can throw trash, you can throw tires, you can throw human body, whatever it is, as long as it's got carbon in it, you can get some energy out of it. So the boilers, especially for like trash to energy plants, which I don't know if those are real popular anymore, you can get steam turbines, and boilers to do that really well, but much, much bigger, much more expensive, a lot harder to operate. A gas turbine, you can have an operator and a control system that can do all that. So gas turbines are far, far cheaper. And we can do hydroelectric, which means that it's a dam. So you have water pushing on an impeller, and it goes there. That's pretty much all you're going to find. You do have some reciprocating engines. Reciprocating engine usually would be a diesel generator. So diesel would be the force, the supply of energy. You can also get natural gas. Most of the time, diesel engines can burn natural gas. It's dual fuel, just like at your house. Some people here, if their parents or they have a house, at one point it burned number 2 heating oil, and that was switched over to natural gas, which is basically just a nozzle change. It's really just a very simple changeover, and it's not a big deal. So it's the same concept at the reciprocating engine. But reciprocating engines are terrible for efficiency because you might be getting 20 to 25% of energy conversion, where if you had a power plant, a gas turbine power plant or a steam turbine power plant was that low, it wouldn't be in business very long. So reciprocating engines are really good for sort of unique applications, like if you need standby power, and you can look around campus and you see these big yellow, usually they're Caterpillar, they're diesel engines. So there's a diesel engine, and then next to it is the generator. They're usually on the same shaft. Anybody know what the fuel tank is on those? Why do you think they're so high up above ground? Because the fuel tank is below. So you have these rails, these I-beams where they're mounted. The diesel generator has to be mounted, and it has to be mounted on a very, structurally and sound object so that it doesn't have a lot of movement. And then below it, you put what's called a belly tank. You put it in between the I-beams, and that's where you have your fuel for your diesel engines. That's at least on campus. I don't think that they run natural gas to any of the turbines here. I don't believe that that's the case. I don't think there's any natural gas on campus other than maybe going to the steam plant. So reciprocating engines, but very small amounts of those, unless, like I worked on a project, this was years ago, American Samoa, which is, thousands of miles from here. That's an island. It's not practical to build gas turbines and steam turbines there. Maintenance on it is very difficult. So why not just buy a skid operated or skid mounted diesel generator set? And it's a more robust one than you see for these standby applications. But as long as they're having diesel fuel sent to the island, they can get the power that they need. So even though you think these islands beautiful, all this natural scenery and all that stuff, they actually have pretty dirty power supplies, unless like you have the Galapagos Islands where they use solar and wind, but people there don't have the same power demands that they would in American smaller. So we'll talk about synchronous generators. If this will move forward. How do you build it? Any AC machine has two parts, a rotor and a stator. The stator is going to be the three-phase winding that we studied when last chapter, when we looked at rotating magnetic fields and we got pole pairs and we figured out the number of magnetic north and south poles. So that's where we're going to have our three-phase windings. On the rotating part, we're going to excite that with DC. And we need it to be DC. And this is the key thing. This has to be a DC winding because we want to make sure that operation of our machine is in sync, means it rotates at the same speed as the magnetic field that rotates around it. Okay. So to build the rotor over here, you need a plus and a minus to go in. Now, you can use a permanent magnet generator, a permanent magnet inside the rotor to do it. But the problem is what we'll learn is with synchronous machines, you can monkey with this DC excited winding to either get reactive power out of the generator or to have it absorb. And so the vast majority of synchronous generators have a DC excited field so that you can boost things up and down. If it's running completely independent from the grid, then you definitely want to control it because the more load you have on a generator, the more the voltage at the terminals is going to drop. Well, one of the things you do, you put more oomph into the system. Remember our equation from last class? Our armature voltage is K times phi times omega. That's constant and that's constant. The only thing we can adjust is phi, which is proportional to the magnetic flux in the machine. So we put more DC, which means it increases the flux. And that's how we can actually get control. So if our voltage is starting to get low on the terminals because of heavy load conditions, we just go ahead and put more magnetic field energy, which means we put more DC into the machine, and thereby the terminal voltage boosts up. The converse of that is if it's you've been running along heavily loaded, and then a big amount of load trips offline sort of instantaneously, then your excitation needs to be adjusted down because you don't want the voltage on the terminals to be too high. And so it's really good if it's running what's called isochronous or independent from a grid. That's another term. There's a newer term because of all the inverter-based technology. It's called grid forming mode. When you think you form the grid, you're actually making it, right? So there's grid forming, which means isochronous, which was the term what it used to be. And then the other one, which is grid following, which means whatever the grid is, I follow along. So one is I'm the boss because I form you. The other one is I follow along is somebody else is the boss. Old terminology, grid forming was isochronous, and grid following was called droop mode because you would have to drop the speed a little bit, drop the excitation depending on the amount of output current or increase it. So how you cool a synchronous machine is pretty much what's going to limit its physical size. Obviously, if you need a 10,000 megawatt generator, you're going to have to order one that can do 10,000 megawatts. And then the designer of the machine is going to have to figure out how to cool it. The bigger the unit, the better you can get, cooling in there within reason, but you would just physically need it. Also, you need more windings. You need more windings because you're having more copper, right? You need bigger copper to be able to handle it. So that's why most of the generators you're going to go buy at Home Depot, 120, 240, you can pick it up and put it in the back of your car, right? But if you're talking about a 10,000 megawatt generator, you're talking about something that's so massive that it needs a lot of physical size. And so at that point, the cooling, you actually might have cooling ducts within the windings. And the voltage that was at the 120, 240, now you're pushing 25,000 volts. And the reason why you're pushing 25,000 volts is no other reason than you're trying to get your current to go down. Okay. Remember the biggest generator that I know of in the Northeast is at Millstone. It's a 1500 MVA generator. That generator's nominal voltage is 25,000 volts, but it's got almost 50,000 amps of current. So you still need pretty massive copper to do it. But if you ran that at 480 or 13.8, then you would need it would not be practical to build a machine that can move that amount of current. Ideally, you would keep going up to higher and higher voltages. And I'm not exactly sure why people stop at 25,000 volts. I mean, there's nothing saying you can't run a generator at 138 kV. It just might not be that the physical spacing, because you can arc across things so easy. It just might be one of those things that it's just physically impractical to design a generator that can run at that higher voltage. So the biggest generator voltage I've ever seen is 25,000 volts. But again, that's 1500 MVA, almost 1500 amps. It would be a much cheaper generator if you could run that at 138 kV or even better, 345. You could get your cables quite a bit smaller. So number of poles or pole pairs, right? Because we only have an even number of poles, is going to determine what the speed is. And believe it or not, the speed is determined by our mechanical engineering friends. Because the mechanical engineering friends have to do all their work to optimize their mechanical system. And they know I can run this generator at 3,600 RPM, 1,800 RPM, 1,200 RPM, et cetera, et cetera, et cetera. So they're the ones who have to figure out what the mechanical system needs to be rated for. We as electrical engineers will only focus on, okay, you need it to be 1,800 RPM, then I know I need a 4-pole machine. 1,200 RPM, I need a 6-pole machine. So that's when you have to work with mechanical engineers to figure out what is the application that you're going to be doing. I can say in most applications, the bigger the power, typically, the more likely you're going to run at 3,600 RPM. So if you're pushing 50 megawatts, it's most likely you're going to be running at 3,600 RPM. I don't know this for a fact because I'm not a mechanical engineer, but I believe mechanical engineers have an easier time getting it to operate, a system to operate at 3,600 RPM than it is for us to reduce or increase the size of the generator. Because remember, power equals torque times omega. If we drop the speed in half, but we want the same power output, we have to double the torque. So now you need a lot beefier equipment because you're handling 2-4 times whatever the value of the torque is. So you really need to be aware of what's happening in terms of that. So our mechanical engineering friends, they need to worry about all that stuff. They'll take care of that. Yes, sir.
Does that 3,600 RPM also have to do with the connecting for it, right?
Yep. Yeah. Because remember, we're always rotating around one cycle, right? And if it's 2-pole machine, mechanically, we have to operate 1 full revolution. And it's also the same thing electrically. Well, this is 2 pi radians per second, right? And if you convert that to radians, right? How many radians? It's going to have to be 377, because if we multiply that by 60 hertz, why do we multiply that by 60 hertz? That's the frequency that we're getting. And then the units will cancel out. And then we end up with, 60 times 2 pi, which is equal to 377. If we have a 4-pole machine, it only has to rotate around half the distance before electrically we start over again. So that's why it spins at 1,800 RPM or 377 divided by 2.
Different RPM.
In Europe, they would run at 3,000 RPM would be their fastest speed that they would run if it's a synchronous machine. Yep. Yeah, because this frequency is not 60, right? It's 50. So run a different speed. So 2 types, salient pole or round rotor. A salient pole is the one we talked about. It has to be, you have to take the individual magnetic material, they stamp it out of a piece of iron, and then they place them together, they line them up, and then they bolt them on each end, and then they compress it, and then they hold it in place. And that allows us to put a lot more poles. Each of these poles is shown here. We just kind of concentrate there. And then we run the windings inside these areas. Okay, just kind of a simple pictorial view. Most of the time, you're going to be slow speed because you don't want to be running this at 3,600 RPM, although you can, you just have to build it to make it more robust. But this is something that's going to run at between 50 and 300 revolutions per minute, or anything 1,800 RPM and less. It's typically what you find. Not always, but typically. So if I tell you you have 3,600 RPM, it's almost guaranteed to be a round rotor. All right. And because you need so many poles, it's just harder to mill a piece of solid iron to do that. So you just build it out of this. It's running at a slow speed. You can physically make it bigger. So now you have a design here. And this is a round rotor design. You can see on the outer perimeter, is where the windings are on the rotor. And they're just located about the perimeter. And even this one shows you have water going in and forcing the turbine to rotate. Water, the fastest one I've seen is about 300 RPM, is the fastest machine that I've seen, hydroelectric facility. And that was a pump storage facility. Pump storage means it takes water from one location and pumps it up top of a hill or top of a mountain. And then when you need it to generate electricity, it drops it through. So this is a pretty big head. The top of a mountain to the wherever the reservoir was could be 1,000 feet of elevation. That's got a lot of energy. So it's spinning at 3,000 RPM is no big deal. Where if you look at the still water, anybody been on the bridge that will take forever to build? But you can see the difference between the top of the bridge and the bottom. It's what, 20 feet maybe? Not very high. So that water goes over the dam, or hopefully it doesn't go over the dam because it's wasted energy. It goes through the dam and you don't have a lot of what's called head. So when you talk about hydroelectric facilities, you talk about head, which is the difference in height between the reservoir and where it goes into the impeller for the turbine. So those might run at 24 RPM, very, very slow. And they're just physically massive because you need so many poles and you need a lot of torque. Here's another application of one. And this one was one I actually we got to do a tour of AC Electric. And this is one that I actually was standing. That's a picture that I took. And you can see the round rotor. I should have taken one from the side, but you can see the windings are located here. They're all crammed in between these poles. If you look really closely, you can see some laminations in here. But yeah, this is, I believe, a 4-pole machine. So this was designed to operate at 1,800 RPM. Anybody want to guess as to what this is? It's another synchronous generator. It's a completely separate one. But this one, because remember, we have to get DC, and notice there's 2 wires over here. We have to get DC into that rotating part. Well, I talked about using brushes and slip rings to do it. You can also get better applications where you can basically tack on another synchronous generator on there, but flip it around. So instead of the stator having the AC output, I make the rotor have the AC output. You say, hey, Paul, wait a minute. You just told me AC output. Isn't this supposed to be DC? Yes. What do you think these things are right here? I've got AC. I want DC. John would be very disappointed. Diodes. Those are just diodes. You take AC out, you run through a set of diodes, they convert it to DC. So you literally put diodes on the shaft, and diodes are pretty, they're pretty robust. They don't break all that often. So you've got an AC machine tacked on to another AC machine. And just for giggles, look at the cooling here. You can see the cooling fins on that. They're forcing air to flow through the machine to improve the cooling. They never look this clean unless it's being rebuilt. Like this is still in the shop, right? You can see it's going to be put in the shaft, but it's got wound. You can see the purpley windings. Remember, that's not purple copper. That's just the insulation on the wires. I wonder if I can zoom in a little bit. I can't, but you can see the size of the conductor. So fairly decent sized conductors. And then they're spaced. And then they're kind of kept together, but all this is like a paper tape. They just tape it around and they keep it in that position. And so that's how they can go ahead and do that, keep it in position. So here's one not too far. This is a actual cylindrical, so round rotor. So the only difference I'm going to do is I'm going to take a solid piece of iron and I'm going to mill out where I want to put the windings. Okay. These tend to be high speed, but also high torque. Because this solid piece of iron, again, I'm not a metallurgist, but a solid piece of iron would seem like it can handle far more torque than something that the shaft, because that's the only thing that can really handle the torque, is just right there, right? That's where everything is mounted to. Where over here, I've got the entire mechanical or the system here that can go ahead and do it. So same concepts. You can see a stator winding and a rotor winding. Those are the windings that live on the rotor. You have a tiny little air gap between the two because the rotor shouldn't be touching the stator. Otherwise it won't spin. So you have to have an air gap between the two. Not too big of a deal. As long as that air gap is not so big, you can get magnetic energy to jump across an air gap pretty easy. So no problem. And this just shows one thing that I didn't talk about the last slide. Direct and quadrature access. That's just a math term. A direct access means it's lined up with one of the North Poles. A quadrature access means in quad with the direct access. So it's 90 degrees in front is what the quad term stands for. And the reason why they use this is when you work with AC machines and you're trying to analyze them a little bit more sophisticatedly, you need to have direct and quadrature access components to be able to model it. Okay, so we won't necessarily need to do it, but that's an idea. And you can see size of the generators up to 2000 MVA. I've never seen anything more than 1500 MVA. I would imagine, anybody know the name of the new hydroelectric facility in China? This is the Three Gorges Dam. Is that it? Let's see if we can find any information about it. So this is a fairly new hydroelectric facility, and they're saying it's so big that it's supposed to be changing the Earth's rotational pattern, I guess, because it's holding so much water there. And let's see, generator size. So these are 700 megawatt capacity hydroelectric dams, which seem big, but again, if you go to, let's see, that was Millstone. This is the one that got upgraded recently. Oops. See, just did it again. I have no idea. It's just here. It doesn't seem to do it in my other screen, my other class. It's not duplicated. But last time it was able to, no problem. Okay. So this is Millstone, and that is a 1237 megawatt generating plant. So that is over 500 megawatts bigger, and that was built in the 80s. So 700 megawatts is a really big hydroelectric facility, individual unit. But again, it pales in comparison because the energy stored in water is pretty good, right? But again, you don't have much head. Whereas when you talk about a steam turbine, because this is going to be powered actually by 3 steam turbines, I think it's 3 steam turbines, that it's got just way more energy in the steam. So the steam is at 600 degrees, there's a lot of volume. You can go ahead and do that. I would imagine in Europe, they have bigger generators, mainly because they use different nuclear technology designs. Nuclear power plants, at least in the US, will always be the largest generators you have because it doesn't make sense to build a nuclear power plant for 50 megawatts. It's so expensive to build one. Why not big it as big as we can? And it gets to the point, you can't just keep upping it because it's just hard to get the heat away from the reactor. So if you have water to pull the heat away, then you can only get so much water moving. But in other places, like in Russia, in Chernobyl, which is actually Ukraine, what they had there is they had graphite as a moderator. So all around the reactor, instead of having water, they had graphite. Well, you can make a huge heat sink out of it, so you can make, excuse me, much larger generator sizes. So those might have been 2000 megawatts or something like that. I don't know. So here is the round rotor, kind of hard to see. This is a stator. That color green looks kind of familiar, doesn't it? That color green there. That's the stator from that salient pole synchronous machine. And you can say, hey, wait a minute, Paul, why are you showing us the rotor? I mean, the stator? The stator is the same. It just has a different number of poles. It doesn't change anything about it. So a round rotor stator is the same as a salient pole. You just divide up the conductors by the number of pole pairs that you need. All right, so how do you get it to work? First thing you need to do, you're converting mechanical energy to electrical energy. So I need some mechanical system to get this thing rotating. It has to rotate, right? Because the generator, all it can do is rotate the rotor inside the stator. It can't move left to right. It just needs to rotate. So there's a prime mover, steam turbine, gas turbine, hydroelectric dam, whatever you want to say. Now that rotating part that has been mechanically rotated has a DC current on the field or going through the wires that in the rotor part. Okay. So that gets a magnetic field that rotates inside the machine. The machine consists of another set of windings on the stationary part, and there are just 3 windings, again, spaced properly. Now you get a magnetic field changing inside of a closed loop of wire. And if you remember from our generator action, when we talked about for chapter 1, that's going to produce a voltage. Okay. And you're going to get a current flow because if you take a voltage and you send it out to a load that's going to allow current to flow, you're going to get current flow, and then that's how you get torque or power out of the machine, either one. So the power is out, and then the torque is the induced torque that cancels whatever the mechanical torque is applied. So synchronous speed means we're going to be running at a specific electrical frequency. So how do you determine the electrical frequency of the speed? Well, this is the mechanical speed of the rotor. And it always is going to operate in sync with the synchronous speed. So if it's going to be 60 hertz, is what we're over here. The only thing that can change is the number of poles. Okay, so if you have P equals 2, we have 60, excuse me, equals 2, n divided by 120. So 60 times 120 divided by 2 equals n sub m, which is 7,200 over 2, 3,600. RPM is the unit. If you have 4, then that becomes a 4, 1,800 RPM. And on and on and on and on and on, right? But a synchronous machine has to operate at the exact speed that the synchronous field is operating. Must operate at the same speed. Okay, that's a very important characteristic of it. Here's how we can actually control that magnetic field. So kind of like we did in lab yesterday, we have a field current, we have an exciting current. In the transformers, it's AC. In a synchronous machine, it has to be DC. And then we're going to produce an armature voltage here. Fixed and fixed, that's variable. So the only thing we can do is pump up the current to change my magnetic field or the flux that I get there. And so I start to increase it. And again, we get linear until some point where I'm trying to get too much magnetic field flowing or magnetic flux flowing through that magnetic core. So now it starts to not be a linear relationship between the field excitation current and what the armature voltage is going to be. So I start to saturate, just like what we saw in lab. Doesn't matter if it's a generator, it was a transformer. We saw how we got some saturation. And so now we start to saturate. And so again, we're going to operate someplace in that region. We're going to be always operating in a saturation region. It's very unlikely that we will ever operate unsaturated unless we're extremely lightly loaded, or if we're running and the machine is absorbing so much reactive power, it could be that we're in the unsaturated region. But here to here is unsaturated, and anything, you know, about the knee point would be considered saturated. And that's important to us because the generator has different performance parameters based on if you're running it in unsaturated or saturated characteristics. And so if you look at, let's see if I can bring up. This is a generator data sheet for a small generator. All right, where are you? Let's try this one. So this is a tiny little baby generator at a hydroelectric facility just up the road here. And let me move this over here. Can everybody see that? TV land, am I sharing the right material?
Yep, I could see it.
Again, I worked on it a few years ago, 2018. It actually didn't get started until 2020 or 2021 because there was a couple mistakes when it was mechanically built. These are mechanical engineers, they make things difficult. Actually, it wasn't their fault. They built it, they were given the wrong dimensions. And so when they put it on, it was like 6 inches too short. And they still tried to run it anyway, and it ended up breaking stuff. So they had to get it rebuilt. So anyway, this is a fairly, because they redid up in Millinocket at the old paper mills. They used to use, some systems used to be working at 40 hertz system. They would run at 40 hertz. But the mill has long since closed. And so they still have all this wonderful hydroelectric capacity that all the dams have been built. It's almost free to run these places. But the grid is at 60 hertz. And so what they had to do for many, many years is they had to put a frequency converter, which meant a fancy dancy static, a microelectronic or electronics device that would convert 40 to 60 hertz. Well, it was expensive, it would consume power, and it would fail. So what they did is they started swapping out the generators. They rewound the generators so that they would run at 60 hertz. And this is an application of a generator that was actually, they took the rotor, and I think they took the whole generator out and they just swapped in a new machine. And so this one is, if you look at it, it's only a 4 megawatt machine, pretty small. But look at the number of, look at the speed of RPM, the rotation, only 240 RPM, pretty slow, right? Compared to the 3600 we're talking about. And there's a whole bunch of data over here, but take a look over here. Remember I told you about saturated, unsaturated? This is actual data from a data test sheet, right? You can see it's dated and who made it. It was made by WEG in the good old US of A. See the flag, but you can see you have unsaturated and saturated. So for generators, you need to have both of those parameters because you need to determine when you're going to be running or what characteristic you need to use if you're doing saturated or unsaturated. Interestingly enough, it only affects the X values. It doesn't affect the R values at all because that's resistance, right? Magnetic energy has no impact on that. It's just going to be the value of X. And so again, you can see real world application with an actual data sheet and go from there. Yes, sir.
What is the service factor?
Our
factor.
Anybody want to guess the service factor? It's another way to say quality of the motor or the machine. So if you have something that's rated for a 1.15 service factor, you have a nameplate, let's say in this case, it's 4 megawatts. But if the service factor is rated for 1.15, you could actually run it at 1.15 times its power output and it would still work. So it's a way of saying this is a more quality built application because it's designed to run at more than 4 megawatts. It's rated for 4 megawatts. That's what you should run it at. But it actually has a little bit more copper in it, a little bit better cooling, perhaps, so that you can get more power out of it if you need to. So it's more of an application for service factor, would be more about motors. Because some motor, if it's 100 horsepower, but it has a service factor of 1.2, you could actually run it at 120 horsepower and the motor should still operate perfectly fine. Okay. Any other questions on this nameplate? This is a pretty basic data sheet, but it's only a 4 megawatt generator. I say only, but in the power world, that's pretty small. Okay, no other questions? All right. So saturation is really important. Real world versus fantasy land, it's the same thing. And the same thing about voltage regulation. We still have to deal with voltage regulation. The difference in voltage regulation now is the amount of reactive power going in and out of the machine has a huge influence on the voltage regulation. And in most cases, if you remember the voltage regulation, V no load minus V full load over V full load, we would always say that that would be, we would always get a boost in the voltage. So we would get a negative voltage regulation. The voltage would float up. Over here, it can go down or it can go up depending on the degree of that. So if you look at the description here, let me move this out of the way. It depends on the power factor. So if you're a lagging power factor, your voltage regulation is going to be positive. If it's a unity power factor, which means no reactive power is going in or out of the machine, it's going to be positive, but very small, almost negligible. And if it's a leading power factor, which means reactive power is coming in from the grid, then our voltage regulation is going to be a negative value. All right, so the last thing we'll do today is models. We did a model of a transformer. We did that in chapter 2. We need to model the AC machine or the AC generator. So we know it's a generator, so we need a power source. And we know there's some inductance because it's a bunch of coil wires. And we also have some resistance perhaps in the coil. So with all that being said, here is our simple equivalent circuit of our synchronous generator. Now, one thing that this part is missing, this is the AC side of the house. In actuality, there's a magnetic field that in here comes your field current, okay? So sometimes you'll see this part added to it because it does influence the operation. But this is DC, remember? This is AC. So these two have no electrical interaction whatsoever. This is going to create a magnetic field. We'll show it as a bunch of waves that are going to impact the magnitude of that. That's all that DC does. It just changes the magnitude of EF. Does nothing else. But oftentimes we don't include it in our equivalent circuit for our synchronous generator because it doesn't have any electrical connection whatsoever. So we don't really need to include it. All right. So there's a couple things we have. Let me move this over here. So over here is what the voltage would be if we didn't include the leakage reactance. Our leakage reactance is right here. And then this is our armature resistance. That's just the coil of wire. You oftentimes, and we'll do that mostly, we'll combine those to have one synchronous reactance of our machine. All right. So the model of a synchronous generator is actually really, really simple. Very, very simple, very, very basic. Have a power supply, one inductor, maybe two inductors, and then one resistor. And then this is the terminal of the machine. That's where you can actually measure voltage. Okay. You can physically walk up to the terminal of the machine and measure voltage. This voltage is very, very, very difficult to measure because it's the voltage that is induced across the windings. So it's the voltage that is back all the way across the coils of wire. So it's a voltage that exists there, but you can't access it. You can't measure it directly. You can measure the terminal voltage. And we need that when we start looking at what are called open and short circuit tests to be able to calculate what that voltage is. So here's our phasor diagram. Very complicated, but don't worry too much about it. It just shows all the voltages. Really, all I care about is here, which is what our internal voltage would be, our terminal voltage, inside or across the windings. And this is the terminal voltage that I have there. This angle, do you remember delta here? If you don't remember it, it's the same angle here. That angle, that delta, is our torque angle. That's actually proportional. Remember the torque is equal to a couple parameters times the sine of the torque angle. That angle here is the same between VT and EF. So that's why we include it, and we can call the torque angle here because it actually is going to tell us how much power we can output. So we're going to learn that by knowing this parameter, and this parameter, and one other parameter, and getting X, we're actually going to be able to calculate the power out of the machine. Okay, so that's why we call it the torque angle or the power angle. And then these other parameters, well, if you notice over here, that's IA times RA. That's the voltage drop across the armature resistance. Notice that it's in phase with the armature current. And then the current of the voltage drop across the two inductors is IA times XS. But don't forget we have a J term. So this has to be rotated 90 degrees. So this is 90 degrees ahead of that, right? because Eli the ice says so. Remember, the current lags the voltage in an inductor. So this is the voltage drop across the inductor, whoops. And the current is down here. So Eli is satisfied because the current lags the voltage in an inductor. And the sum of the terminal voltage plus the voltage drop across the armature resistance plus the voltage drop across the synchronous resistance is going to give us our entire voltage. This image here shows a lagging power factor because the current lags the terminal voltage. If it was leading the terminal voltage, then it would be up over here someplace, and then our system would look quite a bit different. We would also find, and this is important for understanding operation, your terminal voltage is going to be less than your armature voltage in the overexcited case, which means we're dumping bars to the system. And the opposite under leading power factor, or when we're absorbing bars, our terminal voltage is going to be greater than our field voltage. And why is that the case? Because if this voltage is higher than this voltage, Q goes in here, but P is always out. So we just talked about something that's kind of a big deal, but may have been very subtle. Q, reactive power, it flows from higher magnitude to a lower magnitude. Okay. So you always look at the magnitude, whichever one the highest one, which is the higher one, the reactive power should be flowing from the higher to the lower. So even though this is a generator and P is going out, I can still have a higher magnitude voltage on the terminal than I do inside. And there's nothing wrong with that. That works perfectly fine for my generator. More often than not, though, the magnitude of the terminal voltage is going to be lower because most systems in the real world are operated in what's called an overexcited condition. The grid needs more reactive power because we tend to operate more at a lagging power factor than a leading power factor. And then put all three phases together if you need to. We hardly ever do this, but we get all three phases. We show them all together, and that's how we get our three-phase equivalent circuit. This one, though, is a little sneaky. This one's shown as a Y-connected one, and it actually is shown correct that way. Okay. Now, most of the time, you'll never see a diagram like this. Let me pick on Wyatt or Noah. When would you normally see this drawing, guys? You sure? That's a three-line diagram, isn't it? See all three phases? So when you have a three-line diagram, you literally will see all three windings and how they're connected. Let me see if I have, if I can find that here. Do I have a three-line diagram on this one? I don't think I do for that one. Let me see. Here we go. This is Bear Swamp. And this is another pumped hydroelectric facility. And it is, we don't want that diagram. That's a one line. But it's basically very similar to the one that I showed you, the Northfield one, but they only have two generators, not three. Let me try this one. I don't think it's a DTT drawing. Here we go. Noah told me he'd never seen a drawing like that. What's that? He told the fib?
Yeah.
There's not a generator right there. And you can see three wires going in. And this is, it actually shows, and it's kind of a misnomer. It shows these ending. This is not true. This literally is a connection all the way through. It's just a coil of wire. And you can see that this one is connected to a common point. You can see the neutral way down over here. And this right here is a transformer. They call it a ground fault neutralizer. Some of the terms they used to come up with, it's just a step-up transformer. That's all it is. Actually, it's a step-down transformer. And that's how you would actually see all three windings. So what we showed here, whoops, is all three phases, but you would never usually see that. You don't even show the X and the R values because we're not modeling it from a power flow perspective. Remember what we talked about. The whole purpose of this drawing is Wyatt, needs to run a test. He needs to know, oh, okay, well, I need to go ahead and grab onto TA1, TA2, TA3, and TA4 on 2187 or 270, whatever, to go ahead and do some testing. That shows all the terminal connections. But it also shows the terminal connections on the generator. I'm going to really blow your minds if I can find it here. Oops. Let me move this up. Really? You don't work, you haven't worked on generating facilities? Wow. This is the one and only transformer I've seen like this. Took me a long time to figure that out. That's a step-up transformer, 333 MVA. What's weird about this transformer? Let's see if Wyatt or Noah can pick that up. It's an ugly way.
That's the first choice. Ugly.
But this is real. You go to Bear Swamp, this is how it's configured. No, it's 333 MVA. What do you notice about this transformer that, like I said, I've never seen a transformer like this? You can give up. Anybody want to know? I want to guess. You might be able to figure that out. Remember in this class, we talked about transformers? We talked about instrument transformers, right? Look at the current transformers right here. Kind of hard to see because it's thick line, but you see how they're just wrapped around the wires going over there?
Yeah.
Look at the transformers here. Those are wrapped around the windings, but look at the bushings for the transformers. It's a delta connected transformer. These CTs are actually within the physical transformer itself. They're buried in the windings. So normally when you have a delta connected load, you monitor the current like that, right? They're actually, in this case, so they're actually monitoring those as phase currents. They're not getting line currents, they're getting phase currents. Never, ever, 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 ever seen that. That's the one and only time I've ever seen it.
So all the current transformers are inside of.
These right here. It's hard to see because, like you said, it's not a very good image.
I'm just saying, not a very good image.
That's the only time I've ever seen it. And I've looked at generator ones and transformers for many years. It's so rare and unique.
The current transformers buried inside of what?
They're buried in the transformer. This is the transformer.
Buried inside of just another transformer?
No, they're buried in the transformer. So somebody inside the casing, so this right here is the terminals. You can see X1, X2, X3.
Yeah.
So that's where it's on the outside of the transformer. Then the wires go down and they go into the individual transformers themselves. And then they put CTs on those wires. So to access and replace those CTs, they have to take the transformer apart and get in there.
Oh, I saw that one.
Inside the transformer?
Yeah, we had to open up a few panels inside the transformer to see if we could buried inside. You had to get inside. We had Siemens there as well.
Usually you don't want to do that. Usually you just put them on the bushings. It's really easy to change them out.
Yeah.
They're up on the bushings. These are actually inside the transformer.
Yeah.
So, well, maybe that's not that rare. I've been doing this for almost 35 years. And yeah,
Yeah, you're the only two.
I've never seen them. There are advantages to it, but there really is no need to vary them because you can get the information you need from the delta, from the CTs on the bushings. So there isn't really a big advantage. It's got to be delta, yeah. There's no advantage at all to having them buried if it's on a Y.
Right.
But yeah, this is Bear Swamp. Like I said, this is not me.
Someone called like Black Widow.
Fun. But Bear Swamp, if you want to look, Bear Swamp is. Oh. Hydroelectric or pump storage. And all this stuff is, you know, I'm not sharing anything that's confidential or anything because sorry, folks. The advanced technology that this highfalutin university uses just kicked us off the interweb. I'm sitting on the access point, so I'm not far, but it just killed me. So let's try Google Maps again. Let's try Bear Swamp. Yeah, maybe that's what it said. So this is all the way over in Western Massachusetts. So again, you can tell when you see something like this right here, you know, you can usually get that's an outflow. That's the hydroelectric one. So this is probably this must be the reservoir. Oh, here it is. I think it's this one up here. Yeah, this is the actual one. This is all underground as well. So you don't see much, I guess.
I'm not gonna push you on that, but I agree with you.
Well-
It's better than you get.
Well, what should I do? I just dump me off again. Maybe we should end the class, but
That sounds like a really.
yeah. Northfield Mountain is up over here. So this is one huge pump storage. This is twice the size of Bear Swamp. So those are really good. All right. I'm sharing my screen. I don't even know if I'm sharing my screen. Am I back in Zoom? No. I'll share my screen again. Sorry, folks. The internet is not cooperating today. So I was just showing people Bear Swamp is over here and Northfield Mountain is up over here. All right, before the internet completely dies, I better end the class. So any questions? Sorry to kick me out twice, so. All right, if no other questions, have a great day. And I'll see you around. Take care, everyone.